Today's built environment is complex and changing. It requires innovative technology to provide material solutions for design and to inspire groundbreaking concepts for architecture. Technology has produced resins, a relatively new material in the architecture and design community. These materials are helping to solve today's most challenging design dilemmas. Like all new materials, resins can be intimidating without the requisite background information. Today we will share with you our experience on the fundamentals of working with and properly specifying the right materials for your applications. To help you envision how your projects can benefit from these adaptable materials, it is important for you to be familiar with the history of this unexpected design tool.
One of the earliest successes of translucent resins taking the place of traditional materials was from a market that's entirely different than that of architecture and design. It came from the consumer packaging industry. It was a case of the Coca-Cola glass bottle. Here's a product that has one of the most recognized shapes of any consumer product in the world today. It was also a copyrighted shape just to preserve the image of the product. Here's a product also that had one of the first sustainable commitments to recycling. However, you had a product that was very limited. Limited in situations such as wanting to be able to consume it at the beach, at a swimming pool, or at a sporting event. Places where you probably can't take a glass container because it could break. The other limitation was the product was heavy. Special transportation equipment such as trailers and loading equipment had to be developed just to be able to haul around glass containers. You're very limited in the amount of weight you can put into a truck, and therefore most glass containers were loaded on the sides of the trucks. So when you think about it, here you have a world-leading recognized product that's really in demand by pretty much everybody on the face of the earth, and yet you can't always use it. And the limitation was only because of the packaging material. And so the question became an engineering problem to say, how can we overcome the engineering deficiency of the glass container? We still want to maintain the attributes of a clear material, a recyclable material, a material that holds a trademark recognizable shape. So in the early 1980s, engineers came up with a new solution, the polyester Coke bottle. Here you have a product that still maintains the key attributes of the glass bottle. It maintained a recognizable trademark shape. It was a material that was very clear, able to see the product still, and a material that could be produced up into the quantities of 20 billion pounds a year and still have a high commitment to recycling. The polyester bottle overcame the deficiencies of the glass container. It has 40 times the impact strength of glass, but only at a fraction of the thickness. And because of that reduction in thickness, you also have a lightweight packaging material. Now, standard tractor trailers are the means of transportation, and the actual material cost itself was much, much lower. Another unexpected benefit of working with the polyester resin was that the polyester resin had a very high clarity. As you can see, glass has kind of a greenish-like hue, whereas the polyester is almost crystal and diamond-like. So now the deficiencies have been addressed. You can now carry and take that bottle with you anywhere. The polyester bottle was one of those classic examples where resins have taken the place of traditional materials by not just maintaining their attributes, but even overcoming their deficiencies.
and there are many types of resins that can overcome a wide variety of design deficiencies. To be simple, there are two main types of resins, thermosets and thermoplastics.
Thermosets, just as their name suggests, are products that once they are formed, they are no longer able to be manipulated. Thermoplastics, on the other hand, are quite different. Their name implies that they can be formed and molded with heat. It's the thermoplastic materials that offer unique attributes and characteristics for designers and architects. There are four thermoplastic materials we will discuss today: acrylics, copolyesters, polycarbonate, and polyethylene. The first class of materials we'll talk about are the acrylics, otherwise known as polymethyl methacrylate. That may sound a little complicated, but you may know it as lucite, acrylite, or plexiglass. Acrylic was developed around World War II as an alternative to glass. It had excellent optical clarity and is very, very weatherable. In addition, it's very, very lightweight. It's half the weight of glass. Like glass, though, it's very brittle. Also, with certain chemicals, acrylic may be susceptible to crazing, which is micro cracks on the surface. And in addition to that, it has flame propagating characteristics in terms of fire performance. The next class of thermoplastic materials is the copolyester family. A relatively newer material developed in the late 1980s came under some lesser known trade names such as Spectar, Vivac, or ecoresin. As you can see, it also looks a lot like glass. It has a unique quality of being very, very clear, but also being very, very tough, very, very durable. A final and an important benefit of the copolyester family is their ability to be recycled. One of the attributes of polyesters that's well known is that the materials can be used in a lot of applications at the end of life, such as things like textiles, fabrics, or even being put back into sheet materials. There are, however, some deficiencies with copolyesters. If specified with a glossy finish, they could show incidental scratches. In addition to that, for exterior applications, they require a UV protectant layer to maintain performance and aesthetics. Yet another class of thermoplastic resin is the polycarbonate family. You've probably heard of brand names of polycarbonates such as Lexan or Macrolon. Polycarbonates are known in the resins world as the extreme materials. They're used in very durable and demanding applications such as F-16 fighter canopies, safety and security applications such as ballistic glazing or detention and retention facilities. Polycarbonates are known for their toughness, high resistance to temperatures, and their self-extinguishing flame propagation performance. Some of the deficiencies of polycarbonates are that they do struggle with incidental scratching and marring. In addition to that, they do require exterior stabilization for long-term outdoor performance, and they tend to have a slight purplish hue. The last category of thermoplastic materials we'll be talking about today is the high-density polyethylene family. Polyethylene is the go-to material for consumer packaging. It is the most widely used resin on the face of the earth. It has really interesting characteristics in terms of its impact strength and chemical resistance. Take, for example, a visit to the grocery store. Quite often you'll see the most aggressive reagents being contained in high-density polyethylene containers. Reagents such as motor oil, gasoline, bleach, and aggressive household cleaners. Because of that, you know it has excellent chemical resistance. In addition to that, it's extremely tough and extremely durable. It also has the largest commitment to recycling. The recycling numbers for high-density polyethylene are upwards of 35%, which means that literally 5 to 6 billion pounds a year of high-density polyethylene are recycled. But it does have a little bit of a trade-off in terms of the other resin families that we talked about. It is not clear. It is somewhat opaque. Also, the material tends to be relatively soft, which makes it susceptible to marring and scratching. Lastly, even though high-density polyethylene is a thermoplastic, it's not as easy to form as other thermoplastic materials such as the acrylics, copolyesters, and polycarbonates. Once you've nailed down the aesthetic attributes of your design, it's important to consider the material characteristics that will be incorporated for performance. There really is no silver bullet material that can achieve performance requirements, aesthetic requirements, and the cost requirements of every application. For example, you could use acrylic in this application due to its clarity and weather resistance. However, acrylic may not be a good choice because of its low impact strength. The way you consider the performance attributes of any material are by the various physical properties that a material has. That can be done through mechanical properties, thermal properties, and application properties. First, we'll talk about mechanical properties. Mechanical properties really characterize how a material responds to different forces. Impact strength. It's the ability of a material to handle abuse. Think of a hospital bed crashing into a wall, or a sliding door that's been run into by someone. Here we show copolyester being subjected to an impact of 30 inch-pounds of force. As you can see, copolyester has no problem withstanding the impact. In the next example, we'll show you what happens to acrylic, again subjecting it to the same 30 inch-pounds of force. Unlike the copolyester, the acrylic results in catastrophic failure. In polycarbonate, the extreme material can withstand multiple impacts, again and again and again, and still have tremendous results. You see that polycarbonate has nearly 60 times the impact strength of glass and acrylic, where copolyester has nearly 25 times the impact strength at a comparable thickness. Like impact strength, tensile properties also characterize the toughness of a material. You use tensile strength to characterize how a material can be installed in an application, whether or not it's safe to use point supports, or if you can have frameless doors with free-floating edges. A lot of times, polycarbonates and copolyesters will give you the most design freedom. In a first example, we'll show you how copolyester performs in a typical tensile test. As you can see, the material pulls and stretches and elongates, but it doesn't break until it gets to a critical point. As a comparison, here's an example of how acrylic performs in the same test. The material does not elongate and actually results in brittle failure fairly quickly once it yields. Another important property to consider for architectural and design applications is the flexural properties of materials. Flexural properties are typically tell you how much the load can be applied to a horizontal surface before you'll see the onset of deflection or bending. In this case, glass and acrylic have the highest flexural properties, with glass being the most rigid of the materials, having nearly 20 times the flexural strength of any of the resins. Isolating the resins specifically, we see that there is a relative difference between acrylic, copolyester, and polycarbonate. Because of their thermoplastic nature, they're able to be formed into shapes to increase the rigidity. Things like simple radius curves, complex curves, even simple line bends increase the structural integrity of resin-based materials. One other unique feature that can be accomplished and achieved with resins is the ability to have expanded core or structural inserts into the resins. These types of structures allow the material not only to be lightweight, but also very structural and load-bearing. Abrasion resistance. How susceptible is the material to scratching? It's an important consideration when you're thinking of things like transaction counters or high use or high traffic areas. In this test, we're showing what happens to the materials after being subjected to 100 cycles in a Tabor abraser. In the first test, we show how acrylic performs, and we look at the haze on the surface upon completion of the 100 cycles. After completion of 100 cycles with the copolyester and polycarbonate, you can see the relative difference among materials. Acrylic being the hardest, polycarbonate having a moderate level of hardness, and copolyester being the softest of the materials. One of the unique things about resins, however, is the ability to put texture on them. The texture offers a unique feature that's not common with other materials, and that is it has the ability to hide incidental mars and scratches. Next, we'll talk about thermal properties. Thermal properties like surface temperatures, expansion and contraction rates, or resistance to flammability. These properties really describe how a material responds to different thermal or energy conditions. An important thermal property is surface temperature. Surface temperature is a way to determine the highest continuous operating temperature that a material can withstand in any given application. A really important consideration to make for surface temperature is when you think about where and how your application is going to be used if exposed to heat. For example, like an exterior application out in the Phoenix sun, or perhaps your application is something that's going to be fixed behind LED or halogen type bulbs. As we're talking about the differences in materials, this graph depicts the heat distortion temperature of the various thermoplastic resins. This graph basically depicts how polycarbonate, again, an extreme material, has a temperature resistance over 300 degrees Fahrenheit. Because something is able to resist high temperatures, therefore implies that it's also more difficult to form those materials. So for example, in order to thermoform polycarbonate materials, these materials must be heated to temperatures above 350 degrees for them to be thermoformed, whereas copolyester is much more easily thermoformed at low processing temperatures such as 250 degrees Fahrenheit. Another consideration in terms of the thermal properties of materials is their rates of expansion and contraction. Resins, being thermoplastic materials, are more subject to changes in temperature, as would something like glass, which has a fairly low rate of expansion and contraction. Typical cases of expansion and contraction would be an exterior application, whereas during the course of the day, the sun heats the material up, causing the material to expand and then subsequently contract overnight. So having a better understanding of how a design may be exposed to temperature fluctuations really helps you understand how to design the material in accordance with its support structures. For example, a framed system or a channel system, you want to be sure you have ample room for a material to expand or contract accordingly without pushing on or pulling out of the frame. Similarly, with point support systems, you want to make sure that holes are sufficiently oversized to allow a little bit of movement for the material while installed. The following formula provides allowances that should be made in framed or fitted applications. For example, take the longest length of a panel in inches, and you multiply that by the temperature change of the sheet in degrees Fahrenheit. And then you multiply by this amazing factor of 0.00004 to get the amount of linear expansion or contraction in total inches. The degree of expansion and contraction for all the thermoplastic materials that we talk about, acrylic, copolyester, and polycarbonate, are exactly the same. Flammability performance. There are a lot of different ways to characterize a material's flammability performance. It's a very important consideration when you're thinking about where and how much can be used in an interior application. In this experiment, we do a small-scale burn test with a polycarbonate sample. We light it on fire and find that, after time, the flame self-extinguishes. Again, we repeat the same small-scale burn test with copolyester, and we receive the same result. Lastly, we show acrylic in the same small-scale test. Acrylic is different from copolyester and polycarbonate in that its flame properties are not self-extinguishing, rather flame-propagating. What this translates to is in a larger application such as an interior finish, you would not be able to use this according to most building code jurisdictions. The last categories of attributes of a material are really characterized through its application properties. These are very material-specific properties that really define a material's fitness for use in an application. Such properties are considerations of weight or density, UV stability, the chemical resistance, the acoustic performance, or even the insulative properties of a material. A really important application property, and what often results into a benefit of working with resins, is the relative density of these materials in comparison to the glass. All the thermoplastic resins have about half the density as an equivalent piece of glass. Thereby, you reap a lot of benefits in working with the resins when you're starting to think about the structural considerations of installing the materials. Think about, for example, when you have a sheet of glass that needs to be installed 10 feet in the air. That type of an application probably requires specialized equipment to help install the glass, whereas resin, being half the weight, is a lot more easy to handle, maneuver, and to install. Additionally, another benefit results in that for large applications, a lot of cost savings can be achieved by having minimal structural supports or even using lower cost materials for the structure itself. A really important application property that is very relevant to these resins is how they perform in an exterior application or under exposure to UV light. One of the ways we quantify a material's performance under these conditions is through artificial accelerators that simulate high-intensity UV exposure from the sun. What we typically do is we replicate some level of intensity that's usually measured in kilojoules. Roughly about 12,500 kilojoules equals about 10 years of outdoor exposure in South Florida. The other thing that's important is to understand what kind of change occurred after this type of exposure. That's through a measure called the B-star value. The B-star value is a quantifiable measure of the color yellow. This indicates that the material has actually undergone some color change due to degradation from UV exposure. As you're starting to learn, there's a lot of differences amongst different resin materials, especially in comparison to glass. One of the unique properties of acrylic resins is they're nearly transparent to UV light. So essentially, even though acrylic is an organic compound that could be attacked by UV light passes right through it. So as you can see, over the long period of exposure, acrylic and glass have very similar type results. They have almost no color shift at all. Copolyesters and polycarbonate, on the other hand, are very different in their molecular structure in comparison particularly to acrylic, since they're all organic materials. If unprotected, they cross the 5 B-star visual threshold level fairly quickly. Does this mean that copolyester and polycarbonates are not acceptable for exterior applications? Absolutely not. Through material science, we know we can actually screen the UV and protect the polymer below it by incorporating high-power UV absorbers. Think of these UV absorbers as like sunscreen, except they have the additional benefit that they're below the surface. And so these materials aren't washed off in like situations of rain, snow, or even in some cases of scratching. When you stabilize the materials, not only can you offer good impact performance for a period of time, you can offer a good impact performance for a long period of time. And that's something really important to understand, is that not only can you maintain the aesthetics of the material, but you can also maintain the physical performance. Chemical resistance is a way to understand how will the material perform in its application when subjected to different chemicals. The best way to demonstrate the chemical performance of a material is to induce the material with some sort of strain, as we have here. In this first test, we demonstrate acrylic when being subjected to simple nail polish remover. What you see first is the onset of crazing, and then the catastrophic failure of acrylic when subjected to this chemical. We show a comparison of copolyester and polycarbonate. Given the same amount of exposure and strain, the copolyester does much better than the polycarbonate, exhibiting much less crazing. Now that we've demonstrated in detail the various property differences among the thermoplastic materials, it's important to understand how these differences can affect a given design or application.
The vision was to create a floating staircase. The challenge was to find a translucent material with enough rigidity to accommodate a 5-foot unsupported span. The solution became finished acrylic in a custom 3-inch assembly. This achieved the ethereal, dreamlike stairwell. The vision was to create a ceiling feature with fluid movement befitting the study conducted in the aerospace lobby. The challenge was to find a lightweight formable material which could also transmit light. The solution was copolyester.
We knew that we wanted it to sort of have some translucent qualities. We knew that we wanted to do something with light so that it would act as a big lantern in the space. The idea to use resin, I would say, came a little bit later on in the process. We really needed to push these ideas because of who the user was, because this is the aerospace labs at Caltech, and it needed to kind of embody that sort of innovative spirit.
The challenge in this installation was to create a contemporary canopy in a translucent and durable material. The solution was polycarbonate, as it offered extreme toughness for this exterior application. The vision was to create a warm glow in this Lincoln Center Performance Hall. The challenge was to find a shapeable, translucent medium for this sophisticated wood veneer. The solution was copolyester, which allowed for a considerable amount of shaping in a needed thick gauge for this backlit and acoustic application.
We proposed to do a singular skin that was a singular continuous shape. So we went out to many different people who were experts, trying to figure out how to put together a very thin wood veneer with a resin core to create this translucency. And that sort of brings us to the kind of concept of having the wood actually have this kind of softly embedded light, or a kind of blush.
The design called for a ripple canopy reminiscent of seismic waves that could also house solar panels. The challenge was to find a formable material with recycled content able to attach with photovoltaic cells. The solution was polycarbonate with 40% recycled content. The vision for the Star-Spangled Banner was an abstract, translucent, and reflective flag. The challenge was to create a lightweight, suspended abstract flag for installation in the main lobby. The solution was copolyester. Fabrication capabilities of copolyester enabled groundbreaking design potential, as the density of copolyester made it much easier to install.
The Star-Spangled Banner flag abstract was originally not a lightweight structure. It started out originally as a heavy concept that was going to sit on the floor. And only when the project went through a certain phase did we discover that we needed a different solution. So we designed 960 of these pixels, and then we froze that in stainless steel. And these are cable trusses, stainless steel horizontal cable trusses. We were able to tweak the reflectivity of these panels such that one panel is a little more translucent than the other panel. This flag abstract sculpture has immediately become the identifying icon of the museum.